Welcome to the second chapter. In this chapter, we are going to look at chemical families, and we shall discuss the trends in physical and chemical properties within groups and across periods. We have already discussed about the number of energy levels in an atom as well as the outermost electrons. With regard thereto, we saw how to classify elements into groups and periods. Here we shall see how elements in a group show similarities in both physical and chemical properties. We will then discover that this similarity is however not replicated across the periods, and elements in a period will show differences both in physical and chemical properties. So, chemical families. Now, we discussed that elements are classified in groups and periods according to the number of electrons in the outermost energy level and the number of energy levels respectively. Now, elements belonging to the same group are said to belong to a family. We shall look at 4 families, and we use their structures to explain the physical and chemical properties within these groups. The first category of elements we are going to look at are those belonging to group 1. We shall then go and look at the elements belonging to group 2. Then we shall jump all the way and look at the elements that belong to group 7, and finally we shall end up with elements belonging to group 8. Now, in looking at these elements, there are key areas of focus that we shall be dealing with. We will look at the graduation in atomic sizes down the group. We will then compare the differences in sizes of the atoms to those of the ions of each element and explain the differences, because there really are some differences. And finally, we are going to look at the physical and chemical properties of these elements in each group and use the atomic radius to explain the differences in these physical and chemical properties. The first family of elements we look at are those belonging to group 1. Elements in group 1 are called alkali metals. They include lithium, sodium, potassium, rubidium, cesium, and francium. But in this case, we shall consider only the first 3 elements in this group. Their electron configuration are: lithium has 2 to 1, sodium has 281, and potassium has 2881. On the periodic table, you can see those elements are listed in the column indicating group 1. And I know you're just wondering, how about hydrogen? Well, in this discussion, we are going to leave out hydrogen for reasons that will be explained later. And let's look at the atomic and ionic radii of these 3 elements we've just listed. The table on the screen represents this information. Take a keen look at this table and make some general observations before we describe these observations. Now, onto the atomic radii. If you look at the atomic radii, it is clear that the radii is increasing from 0.133 for lithium all the way to 0.203 for potassium. Now, generally, we say that the atomic radius is increasing down the group from lithium to sodium all the way to potassium. Why? As you go down the group, you realize the number of energy levels is increasing, and you can get this evidence from the last column indicating the configuration. The increase in the number of energy levels obviously translates to an increase in the radius of the atoms. Next, compare the atomic and ionic radii of each element. clearly the atomic radii is larger than the ionic radii. Why? Two reasons. One, remember, these atoms form ions by losing the only outermost electron that they have. And this means that the outermost energy level is shed off as well, which will mean that the atom of each element will have one energy level more than the ion of that element. For instance, if you look at this sodium atom, in forming an ion, it will lose that outermost electron, and once it has lost, it means the outermost energy level is shed off as well, and there you have the particle that results has one energy level less, and clearly it has a smaller radius, or it is smaller in size compared to the original particle, and this is a sodium ion. The other reason that leads to a reduced radius is that when the electron is lost, it means the resulting ion has its protons being more than the number of electrons. For instance, sodium atom has 11 protons and 11 electrons. A sodium ion, on the other hand, has the same 11 protons but 10 electrons because one was lost. Now, this means that the remaining electrons experience a greater attraction by the protons towards the nucleus where the protons are located, and thus the ionic size tends to reduce. Why? Because the positively charged nucleus pulls the negatively charged electrons towards the center. Now let us turn and look at the physical properties. And when freshly cut, the alkali metals have a shiny metallic luster which quickly tarnishes due to reaction with air, which forms a layer of oxide on the surface of the metal. The metals are soft and easy to cut, and this softness increases down the group. Why? Because as the atomic radius increase, the strength of the forces holding the atoms together decrease. What do we mean by that? Now, if you look at these structures, on the left-hand side, those are very small atoms that are closely packed, and you can imagine the forces holding these atoms together must be very strong, and therefore the left-hand side is a metallic structure, that of a metal which is very strong. On the right-hand side, the atoms are relatively large, and you can imagine the forces holding these atoms together must be relatively weaker compared to those on the left-hand side, and therefore you can conclude that the metal on the left-hand side is actually stronger than the one on the right-hand side based on the atomic sizes. How about the boiling and melting temperatures? Now, these are summarized on the table that appears on your screen now. Take a keen look at that table and try and make some inferences. It's quite obvious. You realize the melting and the boiling points decrease down the group. Again, this is due to the decreasing in strength of the forces of attracting the atoms together. The larger the atom, the weaker the forces. And therefore, as the atomic radius increase, the forces weaken, and hence the melting and boiling points decrease. Now back to our two structures. The structure on the left-hand side, of course, has smaller atoms, and therefore the forces of attraction holding these atoms must be very strong. They require a lot of heat to break, and that is why the melting point would be very high. Remember, in alkali metals, the atomic radius increase down the group, and therefore the boiling and melting point decrease down the group. Conductivity, and alkali metals are good conductors of both heat and electricity. Conductivity is due to presence of the delocalized electrons in the metallic structure. Take a look at this. Now, you may be wondering, where do these delocalized electrons come from? And the delocalized electrons are the one electron in the outermost energy level that each atom donates into the metallic structure. These delocalized electrons are responsible for conductivity. Now, since they all have one electron in the outermost energy level, and therefore it means each atom donates only one electron into the metallic structure, the conductivity in alkali metals is similar. How about ionization energy? And what is it anyway? Now, ionization energy is the minimum amount of energy required to remove an electron from the outermost energy level. Now, just to remind ourselves, in an atom, the protons are positively charged and are found in the nucleus. The electrons, on the other hand, are negatively charged and are found in the energy levels. Now, there thus exists an attraction between the protons and the electrons according to the law of electrostatics. Now, back to the ionization energy. If an atom has a small radius, the outermost electron experiences a stronger attraction towards the nucleus as compared to that in the larger atom. For instance, if you look at these two atoms, the electron in A is more strongly attracted to the nucleus than B because A is closer to the nucleus and experiences stronger electrostatic attraction. And therefore, removing an electron from A is quite harder than in B. If you look at this, you realize the electron in B leaves quite earlier than the electron in A. Now, in alkali metals, atomic radii increase down the group from lithium to potassium. Now, it is therefore easier for potassium to lose an electron compared to lithium. Now, I repeat that ionization energy is the minimum amount of energy required to remove an electron from its outermost energy level. If you remember clearly, the nucleus is positively charged while the electrons are negatively charged. According to the law of electrostatics, there exists a force of attraction between positively charged and negatively charged particles. If the particles are close together, it means the force of attraction is stronger as compared to a case where they are farther apart. So in an atom, should the radius be large, it means the electron in the outermost energy level is weakly held by the nucleus. It is therefore easier to pull out that electron, and it means it requires little energy, and that is why the ionization energy would be less for atoms with larger radius as compared to those with smaller radii. Now, this concept is important in explaining the reactivity series of these elements. You be very careful not to get confused. This is a very simple concept to understand only if you think practically. So let's reason from what we already know. The alkali metals react by losing the outermost electron. True. The atomic radii increase down the group from lithium to potassium. True. A larger atom loses the electron a lot more easily than a smaller atom. It is easier for potassium to lose its outermost electron more than both sodium and lithium. This is because its atomic radius is larger than that of sodium and lithium. Sodium loses its electron faster than lithium. True. Now, this is the reason why the reactivity of alkali metals increase down the group from lithium to potassium. In simple language, the faster an electron is lost, the faster the reaction. Now, if you got that, let's turn back and look at the ionization energy. If ionization energy is the energy required to remove an electron from the outermost energy level, it means the easier it is to remove an electron, the less the ionization energy, and thus the more reactive the element is. Potassium loses its outermost electron much more easily compared to both sodium and lithium, and we've seen the reasons. Therefore, its ionization energy should actually be the lowest, and it is. Look at this table. Now, be sure you can be able to explain the connection between the atomic sizes, the ionization energy, and the reactivity series. Of course, not forgetting the boiling points and the melting points of elements. You hardly ever miss these questions in an exam. So, carrying this information with us, let's now look at the chemical properties of alkali metals. And we start with the reaction with air. All the alkali metals react vigorously with air. Potassium is the most reactive, followed by sodium, and lithium is the least reactive. When sodium is exposed to air, it reacts with the moisture in the air to form sodium hydroxide. Now, this hydroxide then reacts with the carbon 4 oxide in the air to form sodium carbonate according to these equations. In combustion, sodium burns in air with a yellow flame to form a yellowish-white solid which is mainly sodium oxide. In excess oxygen, sodium peroxide is largely formed. On its part, potassium burns in air with a lilac flame to form potassium oxide, which is a white solid. Now, generally, alkali metals react with oxygen to form metal oxide. You realize in combustion we have focused on the reaction of the metals with oxygen, the component of the atmospheric gases which is most active. How about water? Again, the reaction of alkali metals is vigorous, with potassium, of course, being the most reactive. Lithium floats on the water and a colorless gas is evolved. The resulting solution turns a litmus paper blue, suggesting it's alkaline. Sodium darts on the surface of the water as it melts into a silvery ball. A hissing sound is produced and hydrogen gas is evolved. The solution formed also turns a litmus paper blue. Take a look at the reaction of sodium with water. On its part, potassium darts about the surface producing a colorless gas that burns spontaneously. Potassium vapor burns with a lilac flame. Now, in general, alkali metals react with water to form metal hydroxides, which are alkaline and hydrogen gas. Reaction with chlorine. Alkali metals react with chlorine gas to form the corresponding metal chlorides. The reactivity increases down the group from lithium to potassium. For instance, when hot sodium metal is lowered into chlorine gas, the metal bursts into flame and white fumes of sodium chloride are formed. Lithium reacts less vigorously with chlorine as compared to sodium. Potassium reacts most vigorously with chlorine. Reactions with acids. Alkali metals react with acids to form salts and hydrogen. These reactions are, however, very explosive and dangerous to conduct in an ordinary school laboratory. To demonstrate this, let's look at just one of the reactions of potassium with sulfuric acid. So you know what? We are so done with the alkali metals. If you understood the explanations in this section, the next will be easier for you. The trends are more or less the same with similar reasons. Let's look at another chemical family. Meanwhile, you can check your textbooks on some of the uses of alkali metals and their compounds. The next family of elements that we are going to look at are those that belong to group 2, the alkaline earth metals. Alkaline earth metals include beryllium, magnesium, calcium, strontium, barium, and radium. But we are going to look at the first three of them. The electron arrangement for the first three elements are: beryllium has 2,2, magnesium has 2,8,2, and calcium has 2,8,8,2. Let's now turn and look at the atomic and ionic sizes. And again, just as we did with alkali metals, we are only going to focus on the graduation in atomic sizes down the group. We shall then compare the atomic and ionic sizes of each element. If you look at the table on your screen, the first observation that you make is that the atomic radius increased down the group. And the reason is similar to that in alkali metals, that as you go down the group, there is an additional energy level. Beryllium has 2 energy levels, magnesium has 3, and calcium has 4. If you look at these diagrams illustrating the 3 atoms, you will see an additional energy level as you go down the group that ultimately results in increased atomic radii. Now back to our table. If you look at the atomic and the ionic radii and compare them, you will notice the familiar trend that we saw with alkali metals. The atomic radii are larger than the ionic radii. Again, the reason is similar. Alkaline earth metals form ions by losing all the two outermost electrons, meaning the outermost energy level is shed off. This ultimately results to an ion with a smaller radius compared to the mother atom. If you look at this magnesium atom, the energy level has 2 electrons. In forming a magnesium ion, it will require that magnesium atom loses all the 2 outermost electrons. This ultimately results in the loss of that outermost energy level, and the particle that results has 1 energy level less, and this is a magnesium ion. The other reason is that when the 2 outermost electrons are lost, the remaining electrons are more attracted to the nucleus by the protons. This increased force pulls the electrons closer to the nucleus, thus reducing the ionic radius. For instance, a magnesium atom has 12 protons and 12 electrons. The magnesium ion, on the other hand, has 12 protons but 10 electrons, because 2 have been lost. The 10 electrons will be held more tightly compared to when they were 12. Now, with all that in mind, let us look at the physical properties of alkaline earth metals. And the alkaline earth metals have a metallic luster when polished. Now, this luster, however, quickly tarnishes due to oxidation by air. Before using an alkaline earth metal, it is always necessary to polish it to remove the oxide coating. Magnesium is hard to cut with a knife, but it's, however, ductile and malleable. A ductile material is one that can be drawn into wires. A malleable material can be hammered into sheets. Calcium is brittle and hence it cannot be cut with a knife. A brittle material is one which is hard and likely to break. So how about the melting and boiling point? Now, the table on the screen shows the boiling point and the melting point of alkaline earth metals. Again, the trend looks familiar. Looking at that table, the melting and boiling points decrease down the group. Why? Because the gradual increase in atomic radii means the forces of attraction between the atoms weaken as you go down the group. Important, in metals, atoms are held together by forces of attraction between the positive nucleus and the delocalized electrons. These forces decrease with increasing atomic radii. How? Take a look at these structures that we had earlier on. On the left-hand side, we have a structure of an element whose atomic radii is quite small. Now, because the forces of attraction is between the nucleus and the delocalized electron, for a small atom, it means the nucleus and the electrons are quite close to each other, and therefore the force of attraction between them is very high. This results into a strong bond which is very hard to break, requires a lot of energy, and will therefore have a higher melting and boiling point. On the right hand side, you realize the structure is that of an element whose atoms are quite large in atomic radii. Now, it therefore means that the nucleus and the electrons are quite far from each other, and therefore the force of attraction between them is relatively weak. That culminates into a relatively weak bond, and therefore it requires less amount of energy to break that bond. and that is why the melting and boiling points of alkaline earth metals, just like alkali metals, would decrease down the group as the atomic radii increase. And now ionization energy. And we defined ionization energy, minimum amount of energy that is required to remove an electron from the outermost level to form an ion. But unlike alkali metals, in alkaline earth metals there are 2 electrons to be lost. It is important and paramount to mention here that the loss of the 2 electrons in alkaline earth metals or any other atom that would lose more than 1 electron does not happen simultaneously. Rather, the electrons are lost in succession. 1 electron is first lost and the other one is lost after. It therefore means that we would require the first energy to remove the first electron. Later, we will then require a second amount of energy to remove the second electron from the outermost energy level. In alkaline earth metals, which require to lose 2 electrons, we have 2 ionization energies. The first ionization energy is the minimum amount of energy required to remove the first electron from the outermost energy level. The second ionization energy is the minimum amount of energy needed to remove the second electron from the outermost energy level. Now, is the first ionization energy equal to the second? Now, here is a table on the screen showing the ionization energies for those 3 elements, and clearly the 2 ionization energies are different. Keenly look at this table and you realize a familiar trend. The ionization energy decreased down the group. As the atomic radius increased, the outermost electrons become loosely attracted to the nucleus and hence are easy to remove. The other obvious observation from the table is that the second ionization energy is greater than the first. Remember, we have said that the removal of electrons occur in succession. Once the first electron has been removed, the remaining one will now be held more tightly by the now larger number of protons. For instance, magnesium has 12 protons and 12 electrons. When 1 electron is lost, we get a particle with 12 protons and 11 electrons. But we still need to lose 1 more electron to gain stability. Removing another electron from this particle to form a stable magnesium ion will require more energy. Why? Because there is now a larger number of protons in the nucleus and less number of electrons in the energy levels. The electrons are held more tightly as compared to when they were 12. How about we look at chemical properties of alkaline earth metals, and we start with reaction with air. Magnesium burns with a bright white flame, forming a white solid which is a mixture of magnesium oxide and magnesium nitride. Calcium burns with a faint orange-red flame, forming a white solid which is a mixture of calcium oxide and calcium nitride. Now here is an industrial combustion of calcium. Now, however, the trend in the reactivity of alkaline earth metals when burning in air is not very clear due to the oxide coating on calcium which interfere with reactions. Next is reaction with water, and magnesium reacts slowly with cold water to form magnesium hydroxide and liberates hydrogen gas. The bubbles of hydrogen gas will be seen sticking on the metal. The hydroxide dissolves slightly in water to form an alkaline solution. Calcium reacts with cold water, evolving a steady stream of hydrogen gas, and a white suspension appears in the beaker due to formation of calcium hydroxide, which is sparingly soluble in water. Now, the reactivity of alkaline earth metals increase down the group. With increasing atomic radii, the removal of electrons become more easily, and as you go down the group, it therefore means the reactivity increase. Thus, beryllium is the least reactive, calcium is the most reactive, and magnesium falls in between beryllium and calcium. Now, there's a very interesting reaction that occurs when magnesium reacts with steam. Although magnesium does not react vigorously with cold water, magnesium burns in steam with a white flame to form magnesium oxide and hydrogen gas. Take a look at this. Next is reaction with chlorine, and when a burning magnesium is lowered in a gas jar containing chlorine gas, the metal continues to burn with a brilliant white flame, forming a white powder which is magnesium chloride. For calcium, usually doesn't react with chlorine due to coating by calcium oxide formed when the metal is heated. However, under suitable conditions, calcium may react to form calcium chloride according to this equation. And lastly is the reaction with dilute acids. When a piece of magnesium is placed in hydrochloric acid, there is effervescence. A gas that burns with a pop sound is produced. This gas is hydrogen. Similarly, calcium reacts with dilute acids to form salt and hydrogen. However, when sulfuric acid is used instead, the reaction goes on, slows down, and finally stops due to formation of an insoluble calcium sulfate that coats the metal surface, preventing further reaction. Again, we are done with alkaline earth metals, and we are now going to look at another family of elements that are non-metals. They come from the other extreme end of the periodic table. Next is halogens. The next family of elements that we are going to look at are those that belong to group 7, and they are called halogens. The word halogens means salt producers. Halogens are nonmetals belonging to group 7 of the periodic table. The first 4 halogens are fluorine, chlorine, bromine, and iodine. The electron configuration for the first 2 is fluorine has 2,7 and chlorine has 2,8,7. All halogens have 7 electrons in the outermost energy level and exist as diatomic molecules. Their atoms do not exist independently, rather 2 atoms combine to make a diatomic molecule. Turning to the atomic and ionic radii, the table on the screen now shows the atomic and ionic radii for the 4 halogens. Now if you look at that table, look at the column on atomic radii. The atomic radii increase down the group. Why? Just as we had explained on alkali and alkaline earth metals, this is because as you go down the group, there is an additional energy level which culminates into an increase in the radius of the atoms. Now compare the atomic and ionic radii of each element. Is the trend the same as the one we had seen for the previous 2 groups? No, and in fact it is the exact opposite. For halogens, the atomic radii is actually smaller than the ionic radii. So how would one explain this? The atomic radii is smaller than ionic radius of each halogen. Halogens have 7 electrons in their outermost energy level. They thus form ions by gaining an electron. The ion of halogens is thus an anion. That means it carries a negative charge. For example, chlorine will gain an electron which will join the outermost energy level to complete an octet structure, and is as illustrated here. Now notice that there is no change in the number of energy levels because the incoming electron actually joins an already existing energy level that was not full. It had 7 electrons. Now the incoming electron completes an octet arrangement. So how does the ionic radii increase? The chlorine atom has 17 protons in the nucleus, attracting 17 electrons in the energy levels, correct? On the other hand, the chlorine ion has 17 protons, attracting 18 electrons. The effect of the positive nucleus in the ion is therefore lower. Why? Notice that the incoming electron is entering into a zone that has existing electrons. It therefore experiences repulsion from the already present electrons according to the law of electrostatics, where like charges repel. The repulsive force between the existing electrons and the incoming electron leads to a reduced nuclear attraction. I repeat that for purposes of clarity. In an atom of any halogen, and any atom for that matter, the number of protons equals that of electrons. For instance, in chlorine there are 17 protons and 17 electrons. But for halogens, they form ions by gaining an extra electron. Now, during this process of gaining an electron, there is a repulsion between the electron and the already existing electrons. This repulsive force between the electrons reduces the nuclear attraction and thus increasing the ionic radii. Remember, the energy level is not a physical position, but rather a zone or a region around which electrons revolve. So when there is repulsion, the electrons tend to pull further away from the nucleus, and that is why the ionic radii increase. Physical properties of halogens. Now, chlorine can be prepared by the action of concentrated hydrochloric acid on potassium manganate 7 or manganese 4 oxide. In the case of manganese 4 oxide, some heating is required. Now, physically, chlorine is a green-yellow gas at room temperature. Fluorine is a pale gas. Bromine is a volatile brown liquid, while iodine is a dark, shiny, solid crystal. Solubility of halogens. When a boiling tube with chlorine gas or bromine vapor is inverted in water or tetrachloromethane, the level of solution rises in the boiling tube. Now, this is a clear indication that the gases are soluble in water and tetrachloromethane. The rise in the chlorine tube is higher. Solubility of halogens decrease down the group. All halogens are soluble in tetrachloromethane. When iodine is heated, it sublimes into a purple vapor. Now, this is because the particles are held together by weak forces that require little energy to break. Halogens are non-conductors of heat and electricity. Why? Because they do not have any delocalized electrons. The strength of the intermolecular forces increase down the group. These forces are called van der Waals forces. Thus, the melting and boiling points increase down the group. Again, that's a difference from the alkali and alkaline earth metals, where their strength was decreasing down the group. The other difference, you realize that the forces we are talking about here are intermolecular forces, the forces holding molecules together, joining one molecule to the other. The forces we talked about in alkali and alkaline metals were different because it was the attraction between the positively charged nucleus and the negatively charged delocalized electrons. We will look at these structures when we look at structure and bonding in the next chapter. So now, chemically, how do halogens behave? When a stream of dry chlorine gas is passed over heated iron wool, it reacts vigorously, forming dark brown crystals of iron 3 chloride. Now, usually concentrated sodium hydroxide is used to react excess chlorine to avoid the emission of poisonous chlorine gas in the atmosphere. Now, hot iron glows in bromine vapor, forming dark red crystals of iron 3 bromide. Iodine vapor reacts slowly with iron to form grayish-black crystals of iron 3 iodide. The reactions of halogens with metals to form salts decrease down the group. Why? As you go down the group, the atomic sizes increase. The energy levels increase as well. This means that the number of electrons are increasing as you go down the group. For instance, fluorine has 9 electrons and chlorine has 17, and so on. Reactions, we said, occur by formation of ions. On their part, halogens form ions by gaining electrons. We have also said that the incoming electron experiences repulsion from the already existing electrons. In chlorine with 17 electrons already present, the repulsion is greater than fluorine, which only has 9. Thus, it is easier for fluorine to gain an electron than chlorine. Hence, fluorine forms ions faster than chlorine, and hence the reaction is faster than in chlorine. Usually, in gaining an electron or electrons, energy is released, and this energy is called electron affinity. The electron affinity generally decreases with increasing atomic sizes, and thus the reactivity decreases down the group. Reaction with water. When chlorine gas is bubbled through water, it dissolves to form chlorine water, which is a mixture of hydrochloric acid and chloric 1 acid. This mixture is yellow in color. When a blue litmus paper is immersed, it turns red, showing the chlorine water is acidic. The litmus paper is then bleached or decolorized. The bleaching action is a property of chloric 1 acid. Now, this acid is unstable and decomposes to form hydrochloric acid and an atom of oxygen. The oxygen atom then combines with the natural dye in the litmus paper to form a colorless compound according to this equation. Now, you need to notice that a dry litmus paper cannot be bleached by chlorine. Why? Because water must be present so that chloric 1 acid is formed. So if you immerse a dry litmus paper in a gas jar containing dry chlorine, nothing will happen. You need water. When exposed to sunlight, chloric 1 acid decomposes into hydrochloric acid and oxygen gas. Now, this reaction cannot take place in the dark. Now, what are the uses of halogens? Now, fluorine is a raw material in the preparation of polytetrafluoroethane. Fluorine compounds are also added to water and toothpaste to reduce tooth decay. Fluorine is also used in the manufacture of hydrogen fluoride, which is used to engrave words or pictures on glass. Chlorine is used to make bleaching agents, and the same chlorine is added to water to kill microorganisms in swimming pools, and that is why the water in a swimming pool would appear blue. Chlorine is also used in the manufacture of plastics like polyvinyl chloride. The last family of elements belong to the last group of the periodic table. At the very right end of the periodic table, they are called noble gases. Elements in group 8 are noble gases. They are very stable gases with little tendency to react. Well, there's nothing much to say about these elements, but let's look at them anyway. Noble gases are found as free atoms and not diatomic like halogens. They constitute about 1% of the composition of the atmospheric gases. Now, noble gases include helium, neon, argon, krypton, xenon, and radon. The electron arrangement for the first three is 2 for helium, 2,8 for neon, and 2,8,8 for argon. Helium has 2 electrons and 1 occupied energy level, which is full, and hence it is a doublet. The rest have 8 electrons in their outermost energy levels and are therefore octets. We have already seen that atoms attempt to gain stability by being octet or doublet. Now here the noble gases already have their stable states and need not to gain or lose electrons. This makes them very unreactive since they don't form ions. Let's look at the physical properties. Now, this table on your screen summarizes the properties of noble gases. The atomic radii increase down the group because of an additional energy level proceeding down the group. They have low boiling and melting points, and this is because of the weak interatomic forces of attraction between their atoms. As the atomic radius increases, the strength of these forces increase, and this is why the boiling and melting points of these noble gases increases down the group. They are obviously non-conductors of heat and electricity, and now you know why. It's because they lack delocalized electrons. So what are some of the uses of these noble gases? Argon is used in light bulbs to prevent oxidation by creating an inert environment. Argon is used as an insulator in welding. Neon is used in streetlights and advertisement. Helium, when mixed with oxygen, is used in deep-sea diving and mountaineering. Also, it's used in hospitals for patients with breathing difficulties and those undergoing certain surgical procedures. Now, noble gases is the last family that we are going to look at. Now, if you have noticed, in families or groups, the members of a given family show similar trends both in physical and chemical properties. Now, how is it as you go across a given period? We said elements in the same period have equal number of energy levels. Now, does this equality in the number of energy level reflect any similarity in their physical and chemical properties? Now, you will find the answer is no. We are not going to look at elements across the periods, but we are only going to look at period 3. So we are going to look at the elements in period 3, and we study their physical and chemical properties, or rather the trends across the period. So trends and properties of elements in period 3. So as we start, you and I know that elements in the same group have equal number of electrons in their outermost energy level. Elements in the same period have equal number of energy levels. Now in a group, we know the number of energy levels increase by 1 as you go down the group. Now in the case of a period, the number of energy levels remain constant across, but the number of electrons in the outermost energy level and in general increase by 1 as you move from left to right across a period. You got that? Down a group, it is the number of energy levels that increase. Across a period, it is the number of electrons that increase from left to right. Also, elements in the same group show similarities, or rather we can say they show consistency in their physical and chemical properties. Chemical properties across a given period change gradually. So let's look at period 3. Now the elements in period 3 from left to right are sodium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon in that order. So physically, how are they like? And we start with conductivity. Sodium, magnesium, and aluminum are good conductors of heat and electricity, and this is due to presence of delocalized electrons in their structures. This conductivity increases with increasing number of delocalized electrons. Remember, we indicated that the delocalized electrons in a metallic structure are the electrons in the outermost energy level of individual atoms that these atoms donate into the metallic structure. And therefore, sodium has only 1 electron in the outermost energy level. Magnesium has 2 and aluminum has 3. And therefore, the number of delocalized electrons in aluminum is more than that in sodium and magnesium. Therefore, aluminum is the best of the 3 when it comes to conduction of heat and electricity. Phosphorus, sulfur, chlorine, and argon are all molecules, and thus they are non-conductors. They have no delocalized electrons. Now, silicon is a semiconductor. Its conductivity increases with increase in temperature. Now, the same phenomenon is seen in heat conduction. Now, how about the atomic radii? Now, the atomic radii decreases across the period. Yes, decreases. Notice that across the period there is addition of one electron. However, these electrons all enter the same energy level because we have already said the number of energy levels do not change across a period. The increase in the number of electrons also means that the protons are increasing to maintain the neutrality of an atom. Remember, an atom is electrically neutral. It has equal number of electrons as protons. Now, we say that the decrease in atomic radius is due to increase in nuclear charge. Again, I say the decrease in atomic radius across the period is due to increase in nuclear charge across that period, meaning that the outermost electrons are pulled more and more strongly as you move across the period, and thus the atomic radius decrease. How can you explain that in simple terms? Across the period, we can simply put it that the atomic number increase, which means the total number of charged particles, that is protons and electrons, is increasing. And therefore, a larger number of protons in the nucleus, together with a larger number of electrons, will tend to have a stronger force of attraction compared to a few. And therefore, as the atomic number increase, the protons in the nucleus tend to pull the electrons in the energy levels more strongly towards the center, and therefore reduces the atomic radius. Now, because the electrons enter the same energy level, the shielding effect remains the same as the protons increase from sodium to chlorine across the period from left to right. Oh, what is shielding effect? Shielding effect means that the inner energy levels kind of prevents or protects the outer ones from strong nuclear attraction. Thus, they shield them. So let's look at the structure, boiling and melting points of these elements across the period. Now, the table on your screen illustrates this. So let's try and explain it. Sodium, magnesium, and aluminium all have giant metallic structures and thus have strong metallic bonds which require a lot of heat energy to break. Now remember, sodium contributes only one delocalized electron in the metallic lattice, while aluminium contributes 3. The forces holding the particles together in a metallic structure is the attraction between delocalized electrons and the positively charged nucleus. Now also, aluminium has a smaller atom than sodium, which means the atoms are closely packed in aluminium than sodium. Again, if you remember the structure that we had, the structure that has smaller atoms tends to have a more compact structure and therefore strong bonds. And this is why the boiling and melting point increase from sodium to aluminium. And this is due to increasing strength of metallic bonds. For silicon, all atoms are held together by strong covalent bonds. This is a giant atomic structure and hence the high melting and boiling point in silicon. Phosphorus and sulfur are both molecular, and remember, a molecule is made up of 2 or more atoms. In a molecule, the atoms are held together by strong covalent bonds. However, one molecule is held to the other by weak van der Waals forces. Melting involves breaking the weak van der Waals forces between molecules, which require very little energy and hence the low melting and boiling point. This is a very confusing part which finds most students not able to understand. We have said a molecule is made up of two or more atoms. Now, the atoms forming a molecule are joined by covalent bonds. However, one molecule is joined to the other by weak van der Waals forces. When you want to boil or melt a molecular compound, all you need to do is to break the intermolecular forces, that is the weak van der Waals forces. And these forces require very little heat energy. So do not be surprised that the covalent bonding in silicon results into high melting point, but the atoms joined by covalent bonds in molecular structures, still we see that the molecular structures have low melting points. The reason is because in molecular compounds, boiling involves the breakage of the intermolecular forces, and with molecular forces, they are the weak van der Waals forces. Chlorine and argon exist as gases at room temperature. Now the boiling and melting points are low due to weak van der Waals forces. Now chlorine is diatomic while argon is monoatomic. How about the chemical properties? And we start with reaction with oxygen, and we said sodium reacts vigorously with oxygen to form a white solid, which is sodium oxide. Now this oxide dissolves in water to form an alkaline solution of sodium hydroxide. Magnesium burns with a bright white flame to form magnesium oxide. The magnesium oxide is slightly soluble in water to form an alkaline solution of magnesium hydroxide. When polished, aluminium reacts slowly with oxygen to form a white solid of aluminium oxide. Now the aluminium oxide is insoluble in water. Silicon powder can only burn in oxygen at very high temperatures of 450 degrees Celsius to form solid silicon 4 oxide. The silicon 4 oxide is insoluble in water. Now phosphorus readily burns in oxygen with a bright orange flame to form phosphorus 5 oxide. Now the phosphorus 5 oxide dissolves in water to form an acidic solution of phosphorus 5 acid. For its part, sulfur burns in oxygen with a blue flame to form a gas called sulfur 4 oxide. The gas dissolves in water to form an acidic solution of sulfuric 4 acid, which readily oxidizes to sulfuric 6 acid. Chlorine burns in oxygen under certain conditions, forming acidic oxides, while argon is not reactive at all. Now in general, the three metals in period 3 burn in oxygen to form metal oxides, and these oxides dissolve in water except that of aluminium to form alkaline metal hydroxides. The non-metals except argon burn in oxygen to form oxides, and these oxides dissolve in water to form acidic solutions. The oxide of silicon is insoluble in water. Let's see the reaction with water. Sodium reacts vigorously with water to form sodium hydroxide and hydrogen gas. Magnesium reacts slowly with water to form magnesium hydroxide and hydrogen gas. The hydrogen bubbles will be seen on the surface of the magnesium metal. However, magnesium reacts vigorously with steam to form magnesium oxide and hydrogen gas. Aluminium does not react with cold water, neither does it react with steam. The reactivity of metals in period 3 decreases from sodium to aluminium. For non-metals, that is silicon, phosphorus and sulfur, they do not react with water, neither does argon. Chlorine dissolves in water to form chlorine water, which is a mixture of hydrochloric acid and chloric 1 acid. Reactions with dilute acids. Sodium reacts explosively with dilute acids, and this experiment cannot be done in a school laboratory. Magnesium will react with both dilute hydrochloric acid and sulfuric acid to form a salt and hydrogen gas. When polished, aluminium reacts with dilute acids to form a salt and hydrogen as well. And again, the reactivity decreases from sodium to aluminium. For the other elements in period 3, they do not react with dilute acids. So, how can one explain the reactivity across this period? For metals, the reactivity decreases from sodium to aluminium. Now, several things can contribute to this. 1. Sodium needs to lose only 1 electron to react. Magnesium needs to lose 2 and aluminium needs to lose 3. Therefore, sodium will react fastest after it has lost its only 1 electron, as aluminium loses all the 3. Also, the atomic radii decrease from sodium to aluminium, and hence the electrons in the outermost energy level are attracted at different strength. The electron in sodium is easily lost compared to that of aluminium. Why? Because the atomic radius of a sodium atom is larger than that of aluminium. For nonmetals, they react by gaining electrons. The ease of gaining electrons increases from left to right, with chlorine only needing to gain 1 electron. Therefore, chlorine will react fastest. Also, as the atomic radius decreases, it becomes easier to gain an electron. Why? Because that electron is experiencing attraction from the nucleus of the host atom. Chlorine is therefore the most reactive nonmetal, and phosphorus is the least. Argon is stable and thus does not react. We say it is inert.